In this video, I want to demonstrate how to conduct ANCOVA test in R. Here are the steps to follow. Step 1. Estimate the descriptive summary of the variables. This step is optional. Step 2. Conduct the linearity check. Step 3. Test for the normality of the residuals. Step 4. Test for variance homogeneity. Step 5. Test for regression slope homogeneity. Then, step 6, conduct the ANCOVA test. Here is the non-hypothesis we want to test. Teaching methods do not have significant effect on students' final scores. Controlling for the effect of pre-test scores. That is, if you control for the effect of the student pre-test scores, do teaching methods have significant effect on students' final scores? So let me set the working directory. Like I always tell you, wherever you are in have student environments, it's always advisable to first set your working directory to the right folder. That is the folder that contains the file you want to use for the analysis. So let me set the working directory. To do that, I go to session, then set working directory, choose working directory, then I locate the folder. So the folder I want to set as my working directory is located on my desktop. Then I look for it. This is inferential statistics, then inferential statistics training. So this is the folder where I have my file I want to use for the analysis. I have script and the data set. So let me set it. I will just click open. So it has been set as working directory. So now the next thing is to import data set. To do that, I'm going to run the code in line 23. So let me run that. So the data set has been imported. You can see it in the environment here. So I have data set of 45 observations and 4 variables. So to view the data set, I just run the code in line 25. So now here is the data set. You can see we want to check if teaching method have significant effect on student final score. If we control for the effect of this pre-test score on final score. The next thing is to attach the data set for convenience. So let me attach data set. Then next thing is to load the required packages I will need in this analysis. So here are the 3 packages I'm going to use. So let me load all the packages. So the packages are loading. So the packages have been loaded. Now, don't forget the first step in this analysis is to conduct descriptive summaries of the variables. So to do that, I'm going to use describe function that's available inside package. So the first argument, that is the data frame, then square brackets comma, then I insert the variables, the numeric variables. Okay, so I have pre-test scores and I have final scores here. So what this means is that I'm instructing how to only pick pre-test scores and final score from this data frame. And with this, that is to exclude teaching method for now, for a while. Then I'm not instructing how that you should make sure that it give me the 3 statistics according to the groups. Teaching method 1 to 3. So let me run it now. Let me run this code. So you can see I have my descriptive summary. You can see for each of the method, for method 1, I have the mean for pre-test score, that is 82.53, for final score 85.43. Also the standard deviation, we have 7.78, 8.18. Okay, you have that, and so on and so forth. So variance and the standard deviation and mean are the most important things here to interpret. So we also have for method 2 we have the same thing for method 2. So for method 3, lastly for method 3 we have the same thing. Okay, so now the next step is to check for linearity. So we are going to make use of a scatter diagram to see if there is a linear relationship between the dependent variable, that is final score, and the covariance, that is pretest score. So we are going to use the function ggscatter that is available in ggpubhalf package. Okay, ggpubhalf. So this one is for kkplot uh, and scatter diagram. So let me scatter diagram. Okay. So now, so the first argument is going to be the name of the data set. You can see. Then y, the variable I want on my y-axis, that is final scores, and on x-axis I have pretest score. Then the color, I want it to distinguish. I want it to be grouped into teaching method. Then I had losses, then confidence interval. I want confidence interval. So let me run this. You can see I have my scatter diagram for each of the groups. So for teaching method 3, you can see this for teaching method 3. You can see on teaching method 3. So there is a linear relationship between student final score and pre test score. Also for teaching method 2, the same thing, linear relationship, and for teaching method 3, linear relationship also. You can see their assumption has been met. So the next is to test for the normality of the residuals. So to do that, we are going to run a regression. We are going to run a regression. So we are going to use lm function. It's an R-based function. And we are going to assign the result of the regression to this variable lm model. So lm function, you are familiar with this because we have used this in our previous class. So we final score, that is dependent variable, we run it on the main independent variable, that is the teaching method, then plus the covariate we are controlling for its effect. So we run this. So when we run this, we are good to go. You can see here. Now we are able to run that. So the only thing we need from this regression is the residuals of this regression. So to extract the residual from this regression, so what we are going to do is that we are going to type this variable we assign the result of regression to, then followed by $sign, then we write residuals. So I'm going to run the code in line 45. So when I do that, it's going to help me to extract the residuals. You can see in the environment, residuals have been extracted. Okay, so having got my residuals, so I can now inspect these residuals to check if residuals are normally distributed or not. So I'm going to use two approaches. The first one is visual inspection. I'm using kkplot. So and the function I'm going to use is ggkkplot that's available in ggpubhalf package. This package, package, it has been loaded anyway. So then I type residual. You can see. So if I run this, I'm going to have my kkplot. You can see this is kkplot. Based on this, you can see that these data points are not, majority of these data points are not on this line. They are not on this line. Okay, you can see this one just scattering around the line, but not on this line. Okay, not on the line. So these residuals seem to be non-normal. Okay, so let's confirm that by using a formal test, that's Shapiro test. So to do that, we are going to use an arrays function, that's Shapiro.test resid. So we are going to put resid in the argument. So let me run that. So you can see this is the result. We are only interested in the p-value. You can see the p-value here is 0.025, about 0.025. So this p-value is less than the conventional level of significance, that is 0.05. So because of this, we are going to reject the non-hypothesis of normal distribution. So we are going to conclude that these residuals are not normally distributed. Okay, so but we shouldn't worry about this non-normality of the residuals as long as our sample is equals to or greater than 30. We shouldn't be worried about the non-normality of the residuals, because when data sets when sample is at least 30, so we uh, tend to ignore the non-normality result we get, because the ANOVA is robust to um, deviation from non-normality, especially that when the observation is at least 30, is at least 30. Okay. In this case, we have observations, so we can maybe verify we have 45 observations. So we shouldn't be worried about this anyway. Okay. So the next thing is we are going to check for variance homogeneity. To do that, we are going to use Levin test that's available, Levin test, and the function we are going to use Levin underscore test that's available in our status package. That package has been loaded. So we have teaching method. We have teaching method. Okay. We have score. So this is not score after anyway. So it's final score. So let me correct that. Final score. Final score. Okay. So now, because the residuals are not normally distributed, okay, so it's even centered around the mean. So we are centering it around the median anyway. Median. We are centering around the median. So now let's check if the variances are equal across the groups. You can see the p-value, I'm interested in the p-value here. The value is greater than 0.05, so we cannot reject the non-evidence of equal variances. So we are going to assume that variances are equal. So that is our conclusion. So the assumption has been met. So the next thing is to check for regression slope homogeneity. To do that, we are going to use the function ANOVA underscore test. Then the first argument is the name of the data frame. Then the dependent variable, we are running on the main independent variable, that's the grouping variable. Then we are interacting with the covariates, that is the control variable. So the idea is that after running this result, we are going to check the interaction effect. So if the interaction effect is not significant, so that means our assumption of slope homogeneity is met. Okay, so we don't want the interaction to be significant. Anyway, so let me run this. Yes, you can see here that this interaction, we are only interested in this. The p-value here is 0.534 anyway. So to see it clearly, so this one is in standard form code. Let's convert it away. So we can use these function options. So then 7, then so we can put this 99 or change to any other figure. So if I run this, then I will run this. So I'm going to have, you can see 0.534. Okay, this is not significant. Okay, so we are happy it's not meaning that regression slope homogeneity assumption is met. Okay, so now we can now conduct the ANCOVA test. ANCOVA test. So when we are conducting the ANCOVA test, we are going to exclude the interaction. So we are going to use the same function, ANOVA underscore test, then the same argument. Okay, the only difference is that we are going to remove this interaction, so but we are going to add plus. Though we want an effect size that is we have 1 partial eta squared anyway. So we are going to run this. Let's run this. So when we run this, we can see that the pretest score is significant. This confirms our need to control for the effect of pretest score on the final score. Okay, so now let's see our main variable. That teaching method is also significant. This also confirms that teaching method have significant effect on final score. Final score. Okay, you can see the partial eta square. This is large. It's large. You can see anything that's greater than 0.14 is considered to be large. Okay, you can see 0.806 is large. Okay, so the effect size is large. Okay, so now When we are done, we can now proceed to post hoc test. So we are going to use Turkey's honestly significant difference test. Okay, that is Turkey HSD. So the function we are going to use is the function we are going to use is Turkey underscore HSD. Then the first argument is going to be our LM model. Mind you, we have our LM model, so we don't need to rerun the LM model here. So this model. So, so we are going to, this is what we assign the result to. So LM model, so that will be the first argument. Then which is, because we are only looking at the teaching method. So which we are writing teaching method. Okay, we are excluding the control variable there. So you now run this. So the essence of a post hoc test is that, mind you, we found that teaching methods have significant effects on final score when we control for pretest score. Okay, but now because there are more than two teaching methods, if there are only two teaching methods, we don't need to conduct any post hoc test. But we have more than two teaching methods, so we need to check where the difference lies. For example, it may be that only two groups are responsible for, there is the difference in only two groups is responsible for this significance we observe here. Okay, that is the essence. Now, we can see that the difference, that is the difference between the method 1 and method 2, you can see that the student score between method 1 and method 2, okay, the difference is 2.20, okay, and which is significant. You can see it is significant because 0.0341 is less than 0.05, so this is significant. But method 1 and method 2 is not significant. The difference is not significant. Method 2 and method 3 is not significant too. Okay, you can see the signal difference we observed here only comes from the signal difference between method 1 and method 2. Okay, thank you.